So when I say plastic mechanical properties, I don't mean the mechanical properties of plastic. I mean the mechanical properties that have to do with plastic or permanent deformation. So those are things like strength, hardness, ductility, toughness. And in order to do that, I'm going to say this over and over again, but in order to do that, creating obstacles. Location, motion. So maybe one new illustration of that would be, I'm not going to put a reduced cross sections because it makes a more complicated image, but if I pulled on this, the way that it gets longer is not bonds breaking in the direction of stress. The way it gets longer is by planes of atoms sliding past one another because of dislocations. And so what this ends up being is, let's see if I can do this. That's a really not good image, but it's the best that I can draw. Hopefully you can see that this thing gets longer because there are planes that slide past one another in the metal. These particular planes sliding past one another to allow for extension, allow for deformation. So this is an image of unique planes slide past one another in unique directions. So permanent deformation happens when these unique planes slide past one another in unique directions. When I say unique, I just mean that FCC planes and directions are different than BCC planes and directions. So we'll see that, we'll see the effect of that next time. And this motion, this is the equivalent of dislocation motion. So these things called dislocations move on the planes in those directions to allow for deformation. And the best illustration of what that kind of looks like is that illustration I gave you earlier about moving a long, heavy runner across the floor, and it takes too much stress just to move the whole thing because of friction. But if you can put a little ripple in it and just let that ripple move down, then it's easier. Think of that ripple as a dislocation. And that dislocation is going to move on, in this case, on the plane of the floor in the direction of the runner. So if I could do something to keep that from happening, like maybe there's a heavy piece of tape at some point holding two pieces of that runner together, and it won't bend like your little ripple, it'll stop there. Similarly, if I can stop those dislocations from moving in a metal, it will take more stress in order to get deformation, which is the same as saying it's stronger. So these things these obstacles to dislocation motion, we've talked about one of them. Point defects. And those point defects are the same as impurity apples. And that method, that process, is called solid solution strengthening. So we've just finished talking about the process of solid solution strengthening, or alloying. There's two other kinds of obstacles. One are line defects. That's what we'll start talking about today. And the other are surface defects. You've finished that, and today we're going to start talking about line defects. So imagine, as you're trying to move this runner, that there's a perpendicular wrinkle in the rug already. And so as you go, you encounter that perpendicular wrinkle that might prevent you from being able to move it any further. Yeah? And that perpendicular wrinkle is really just the same as the one that we're trying to move. In our case, for metals, it's called a dislocation. So if I have a dislocation ahead of me, and I'm trying to move this dislocation, and they hit one another, or they get close to one another, then that dislocation is an obstacle to the dislocation I'm trying to move. So line defects, point defects are impurity and defects. Line defects are dislocation. And that can be just a bit confusing, because the thing that we want to be able to move through the metal in order to have deformation is the same as the obstacle, because they can be obstacles to one another. All right? So, let me give you 1 minute to make this sketch. Don't feel like you need to copy it. But I just want to show you what happens with dislocation motion. Okay. So this might be the matrix of, we're looking at the face, looking at crystal, and so it goes back in, into the board. And there's atoms going back into the board. And you'll notice that this atom and this atom are missing a bond. And we might even look at it this way. Here's a plane of atoms, and here's a plane of atoms, and here's what we would call a half plane, kind of wedged in. And there's another one right here. Okay? So this atom here, and everyone behind it, that line of atoms, all of which are missing a bond, that is the dislocation. This line of atoms and all that are behind it is a line defect, a 2D defect, a row of atoms all missing a bond underneath. See that? All right, so let's say I apply a shear stress. And by the way, permanent deformation happens because of the shear component of an applied stress. So I'm applying some shear stress, and once that stress gets big enough, this bond breaks. This bond breaks, and this bond forms. And of course it straightens out, and now my dislocation is here. Okay? And then this bond breaks, and that bond forms, and now my dislocation's here. See that? And then this bond breaks, this bond forms, then this bond breaks, this bond forms, then this bond breaks, this bond forms, then this bond breaks, and this bond forms, and now I have two dislocations right next to one another. See that? This dislocation is an obstacle for that to move forward. Okay? So that's how obstacles are dislocations are obstacles to one another. And once that happens, there's no more deformation unless the stress goes up. Okay? So what's causing the strength, increased strength, is deformation. By deforming the metal is getting stronger. And the classic example is if you try and bend a paperclip one way and then try and bend it back to the way it was before. The place where it's bent is now stronger than just above and just below it, and so when you try and bend it back, that place won't bend, but something just above or below will, and you'll get this sort of, I can't think of the word, but you know what I mean. So this is how line defects or dislocations are strengthening. So if I can get more defects in there, if I can put more dislocations into a metal, I can essentially make the metal stronger. And the number of dislocations goes up as I do permanent deformation. So for adding impurity atoms, I did solid solution strengthening, I did an alloy. For adding dislocations, this is either, you could call this cold work, cold rolling, or strain hardening. And the percent cold work, or the percent deformation, correlates to the percent increase in strength. And so, if you look at this handout, which is the homework, there are a couple graphs on there. First one shows, as the percent cold work increases, the yield strength, that's the left y-axis. They're both yield strength. Oh, there's just 2 units. The yield strength also increases. There's PSI on the left and megapascals on the right. So as percent cold work increases, strength increases. So we have to weigh how do you measure percent cold work? 2 possible ways. If I have a plate, and I'm going to put it through a rolling mill to make it thinner. If it's wide enough to begin with, then the width doesn't increase. Clearly, the thickness does. So we might call that the final thickness, and we might call this the original thickness. That's one measure of percent cold work. It's just T original minus T final over T original. The other measure, and these are not related, you use the one if you have sheet, if you have a cylindrical material and you're putting it through a die to make the diameter smaller. You're putting it through a die and you're ending up with a smaller diameter. This is the original cross-sectional area. This is the final cross-sectional area. Percent cold work is equal to original area minus final area over original area. Notice that the diameter is squared in these cases. This area is pi d squared over 4 original, and this is pi d final squared over 4. So if I put this in terms of the diameter, that would be diameter original squared minus diameter final squared over the diameter original squared. Both cases it's a percentage, but just notice that when I'm doing a circular cross-section, I use area. When I'm doing a flat plate, I use thickness. Okay, so if you look at the image on the left, you have percent cold work, and how that's measured depends on the geometry of the part, and you have the resulting yield strength. Steel is unique in that you can get a lot of strength increase with steel up to a point, and then there's not much more. Whereas you see with brass and copper, there's a continual increase with percent cold work. In all cases, the picture on the right tells you the cost involved with doing this. The problem with using this method to strengthen is this method also makes something brittle. Which is why if you continue to bend the paperclip, it breaks. So you see that I can increase strength, but at a cost. I lose ductility. Now, this can be a little confusing because the ductility is measured as a percent, just like cold work is. So the ductility is the percent elongation possible before it fails. Or fracture, I guess I should say. So it is a characteristic. The percent that I could elongate this material before it fractures, ductility. The percent I have changed its shape is percent cold work. Okay? They're different. But it can be kind of confusing because you're thinking about something getting thicker or thinner, and percent elongation can sort of trip you up. So, best way to learn a thing is to try it. So let's look at number one here together. I have a piece of copper rod. It's cold worked, or typically this would be called drawn, from a diameter of 15.2 millimeters to a diameter of 12.2 millimeters. So what will its tensile strength and ductility be? First thing to note is talking about copper. So we need to determine what is the percent cold work. And this is a round cross section. So it's the change in this diameters squared over the original diameter. So let's go ahead and put that all there instead of just relying on, it's the A original minus A final over A original. We could go in and calculate the cross-sectional area of these and then put it in there. Or we could write this as the diameter original squared times pi divided by 4 minus pi diameter final squared over 4 over pi times diameter original squared over 4. And all those pi's and 4's cancel. And I have original diameter 15.2 squared minus 12.2 squared divided by 15.2 squared. Now, this isn't the same as 15.2 minus 12.2 quantity squared, you know that. So I have about 36%. Is that right? Did anybody else get that? Okay. That's 36% cold work. So now, this was copper. I can look at this graph. Note that megapascal is on the right y-axis, not the left y-axis. So I've got, this is copper. If I have 36% cold work, that looks like it's maybe, that's 40, that's 50, so maybe 44 or so. Granted, this is just an estimate. About 44, hold on. No, I'm sorry, I was reading PSI. I want to read at megapascals. So 36, about here. Looks like it's right about 300 megapascal. And looking at that same point for copper, it looks like I'm maybe just under 10% ductility. Maybe more like 7. Or its ductility. That's not good. I mean, that's about bottom there. Now, I'm not told the condition of this piece of copper before I started to deform it. I'm assuming there was no cold work in it. If there was, then what I'm doing is adding to that percent. So if I would start, if it said, okay, this has already been cold work 10%, then my end result here is 46% cold work. Okay? All right, so let's go ahead and look at, let's see, is number 2 the best one? Actually, I want to do one that, I just need to kind of predict what my answers are going to be here. We'll do grass. Okay. Given brass plate that is, we'll say, quarter inch. Oh, I know why I didn't choose. Quarter inch is about 6 millimeters. So let's say it's 6 millimeters thick. Is to be rolled to a thickness of 4 millimeters. and at least (250 megapascals strength. Okay. So first thing we could do is say, oh, let's see if we can do this in one step. So I'm going to say I'm going from 6 millimeters to 4 millimeters over the original 6 millimeters. That's my percent cold work. So 2/6, that's 33% cold work. Right? Okay, what at 33% cold work, what's the ductility? And what's the strength? Okay, 33% cold work. This is brass. I got a strength of around 400. So that's good. 33% cold work, I've got a ductility of about 10. That's not good. Olivia,
How come you didn't swear to them?
because this is thickness.
Okay.
So you only square it if it's round, if it's a
Okay.
diameter. Okay, so I can't do this in one step. So what I do then is I look at my final dimensions and how much cold work I'll allow and work backwards. Okay, so since one round of cold work results in too small or too low a ductility, this process will take at least 2 rounds. All right, 3. What percent cold work will give me both strength greater than 250 and a ductility that's at least 20% elongation. So in other words, let's start with my final dimension and figure out how much cold work I'm going to do on that last step. So I'm going to just try and sketch here just the brass part. And I want 250, so it's going like this, and 250 would be like right around here. Thereabouts. And these intersect at straight edge. can get 250 on grass. I'm gonna say at about 8% cold work. That's where they cross. This is, so that means, this is my 250, that's what I want. That means I need to have a percent cold work that's at least 8% in order to meet my strength requirements. All right, now if I look at ductility versus percent cold work for grass, and a good one here. Grass kind of looks like that. And I want 20. It's about there. And that lines up with, for grass, about 20. Can we see that, where those cross on your graph? So that means if I want more than 20% elongation in my ductility, I need less than 20% cold work. In order to have something bigger than this, I need to be less than 20% cold work. So this is kind of one of those situations where there's potentially a number of answers. So, percent cold work necessary. Get at least 250 megapascals field strength. And at least 20% elongation ductility is 8 to 20%. Okay. Usually, if I don't want to have to spend a lot of rounds getting my desired properties, I'll choose something on the bigger side. So let's say, I'm not going to go with 20, let's say we go with 16. There's nothing magical about that number, but I chose a number between 8 and 20. Final percent cold work as being 16%. All right, and I know my final thickness has to be 4 millimeters. So the last step P would be, well, we'll solve for that. P0 minus 4 over T0 has to be equal to 16%. So, T0 minus 4 is equal to 0.16 E0. So 0.84 T0 is equal to 4. What's T0? What do you get?
4.76.
We'll say 4.8. All right. So what do we know at this point? We know our final product is 4 millimeters, 250 megapascal or more. And 20% elongation or more. The step before that, we'll call it, I don't know how many steps there will be. Step 2, I don't know, shouldn't be 2. Let's pick 4. And we might not end up with 4 steps. But in step 4, I need to have 4.8 millimeter diameter. So that I get a 16% cold work. Yeah? Before I do that cold work, there has to be no cold work in the sample. And so step 3 is the same dimension, and I'm doing, more space. Before I start that step, I need to anneal. Annealing gets rid of that cold work. Okay? Now, if I'm not giving you a restriction about how much cold work I can put in between, and I could say, okay, well, I'm going to go, this is going to end up being step 1. 2, 3. So step 1 is to go from 6 millimeters to 4.8. And it will have some amount of cold work in it, right? And we can figure out how much that is. Is 20, see, 1.2 divided by 6. Just 20. Yeah, right? So my process is, take my 6 millimeter, take it down to 4.8, get rid of the cold work, and then my last step will give me the properties I want. That's it. Okay? Any questions? All right. I think that's a good stopping place. We will take a 5 minute, and then we'll start the exams.
If you take 20% cold work, do you sum them up on each step, or do you, how does
No, because you anneal between each step, so you get rid of it. So I had 20% cold work here, then I anneal, now I have no cold work.